Module 15, SQL Injection. What is SQL Injection? Well, we know from our last session that web application attacks often have a common denominator, and that common denominator is the acceptance of user-supplied input that quite often is not sanitized or vetted or checked for appropriate length, and it just kind of floats on by. And the attackers rely on that to sneak something past the gatekeeper and alter backend queries, inject commands, et cetera, et cetera. So SQL injection, why bother about SQL injection? Because it leads to things like authentication and authorization bypass, our information disclosure, compromised integrity and availability of data, and potentially remote code execution. So let's take a look. We're going to kind of recap our discussion of the post request and a little bit on the vulnerabilities in the source code. So on my 2022 machine, I'm going to target my victim SQL bank, Coastal Bank SQL demo injection page. I'm having some problems with the periods here. All right, the client2.htm, and this is just a standard login page. But the problem is that I can actually enter input. And the bigger problem is that the input is not vetted or sanitized before it's passed back to the verification process, which is used to determine whether my account credentials I've entered are valid or not. So if I was to put in a single quote, that single quote tests the sanitization of the supplied input. In this case, I get an error message back, right? The error message indicates I was able to break something, which typically indicates that they're not really looking at the input. Otherwise, this should have been stopped dead in its tracks. So the error message tells me I've got an unclosed quotation mark before character string and password equals in SQL login ASP line 5. And on top of that, it's a Microsoft ODBC SQL Server driver. So that tells me it's a Microsoft SQL Server, and that tells me exactly what kind of syntax to use and what my basic database structure is going to be in a default installation. All right, so we know we can break something. So we're going to back up and we're going to examine the source code of the page. I'm going to right click, view the page source, and here's the problem right here. I can post, to login ASP, submitted input, excuse me, of username and a submitted input of password, and those are dropped into a SQL query on the back end. All right, generally those SQL queries will execute with an elevated or escalated privilege, and that gives the attacker too much ability above and beyond what they could normally do with just a password-based verification. All right, so on the receiving system, I'm looking at the SQL folder, the login ASP page, open it with Notepad. All right, that shows me a select statement from the user info table where the username equals the submitted username and the password equals the submitted password, excuse me, submitted password that I entered into the fields and the post request on the source code of the page. All right, so when I take a look at the actual database, and again, I'm using an older, very simple web application for ease of illustration. You'd have the same issues in a current app. It's just a little bit more convoluted, and the source code and all that's a little bit busier and more difficult to kind of get your head around if this is the first time you're seeing this. So user info, I'm going to right click, open table, return all rows, and I've got Bob with a password of password, and I've got Alice with a password of password. All right, so that's what the application is expecting. All right, if the submitted username and password matches a username and password pair in the table, it's going to log me into ebanking.asp. If it doesn't, it's going to redirect me to bad logon ASP. So let's test that. All right, I'm going to put in Eric and password. I get denied. And that is the expected result. I didn't submit a valid username and password. All right, I'm going to put in Bob and password, and I get in. All that's really happening here is I'm asking a true or false question. Does what I submit match? Yes or no? If it does, log me in. If it doesn't, don't log me in, but I'm asking a true or false question. So I could potentially bypass authentication authorization bypass by hard coding the query to return a true response. So now instead of Bob or Eric or anything else, I'm going to do a quote or 1 = 1 tac. Get rid of the password. Going to copy that and submit. Whoops, back up. 1 = 1, not 1 tac 1. And I get logged in. That's probably not good. Nope, it's probably not. What's actually happening is instead of putting in a valid username that matches a username and password pair in the table, I'm putting anything in or 1 = 1. Whoops. Tac, 1 always equals 1. So I'm asking it, hey, did what I submit match, or does 1 = 1? If so, log me in. 1 always equals 1. It's a condition that's hard coded to always return a true response. Now, anything that rings true will work. 1 = 1 actually does a lot of other stuff, returns multiple results on a page, and there's other examples of 1 = 1. But in this case, we're doing an authentication bypass, and it logs us in. So this is called an input validation or authentication bypass. All right, so that's one example of injection to bypass authentication. Now, depending on how the application is set up and the web page is coded, it may or may not be set up to disclose information that I request through a query, or I may need to drop it somewhere where I can actually browse to it to retrieve it. So, for example, on this page, I'm going to pull up my skeleton script of SQL Injection Demos. I'm going to back up. And since all this is really set up to do is give me a bad logon or an e-banking, it's not set up to return or transport the results of a query back to me. So if I want to get the results back, then I might have to drop the results to a file and then browse to the file. Now for my single tick ODBC here, I know it's Microsoft. So I can go with Microsoft syntax and I can specify the master database, which I know is always there in a Microsoft SQL server. Use master, execute stored procedure, make web task, call it inetpub www.root db.htm. The kicker there is the www root folder, which means I'm going to publish this to the web server. Yep. I'm going to run a select star from sys databases, and then the whole thing is cut off with the tac, which is always a comment character. Single tick, semicolons, stack your command lines or queries in succession, cut the whole thing off, completely hijack the query. All right, so now when I submit, access is denied. It didn't work. Actually, it did. The page logic behaved exactly as it should. I did not submit a valid username, but it did run. And if I browse to it, db.htm, looky there, there's my databases. All right. So now I know that Coastal Bank exists. So now I'll specify use Coastal Bank, and I'll map out the tables. All right, same thing, exec stored procedure, make web task. This time call it tab.htm and populate the results of the query for sysobjects. Hit submit. And this time tab.htm. And there's my tables. Scroll on down, look for something interesting like, ooh, user info. Well, all right. Credit card, that's probably pretty interesting. So let's take a look at the credit card information. All right, again, basically the same syntax. Run a query, call it credits.htm, select star from credit card. Submit. Credits.htm, well, looky there. Card name, card number, expiry date, and codes. Now, quite often, sensitive information like that is not encrypted, which is a horribly insecure way to store data, but it happens all the time. Certain regulations like PCI compliance require it. It doesn't mean that it's always done. Okay, user info. This is how the have I been pwned databases and the like get compiled. All right, when you use the same credentials on more than one website, and one of those websites is compromised, those credentials may get distributed in the hacking underworld. They may be thrown into these giant databases of captured credentials, like have I been pwned. Then they get engaged in credential stuffing attacks where they start just blasting them at various websites, and hopefully that user's got an account somewhere else and I'm going to find it. That's what credential stuffing is. So there's things like password spraying, credential stuffing, which are different methodologies or techniques for trial and erroring on different websites. The kicker on password spraying is that you don't use the same user account multiple times to get it locked out. You use the same password with multiple user accounts and you keep rotating through it. So you're less likely to trip lockouts. And in credential stuffing, you're just blasting them to different sites. You're only doing one set of credentials. There's no danger in locking out the account. So select star from user info is going to give me, again, access is denied, but user.htm, there's Bob and Alice and their passwords in the clear. That can't be good. No, it's not. Now that I know that the user info table exists, I could actually add an account using an insert. So for example, insert into user info, values of my choosing. All right, so I'm going to add a username Eric and a password of X, hit submit. Access is denied. However, when I verify it on the server, looky there, Eric with a password of X. So I can then log in under that account. So I can create user accounts in the application. I can create user accounts in the database management system. I can create user accounts on the underlying operating system, which I'm going to do here in just a second. All right, so far, why bother about SQL injection? Well, I think those are pretty good reasons to bother about it. Authentication, authorization bypass, information disclosure. Let's do some compromised integrity and availability and a little remote code execution. All right, so I'm going to back up, and this time we're going to use the extended procedure command shell, which these stored procedures and extended procedures may or may not be enabled. It depends on the application and it depends on the necessity. These give us functions above and beyond normal SQL queries, which add to the functionality and utility of the database management system. So I'm going to grab, first off, we're going to take a look at the original site. I programmed that myself. This is the original site. That's the original non-defaced website. All right, I'm going to turn that into you are hacked by using an insert statement and a command shell, XP command shell function. All right, and all that is an echo into the default.htm page. Hit enter. Again, it tells me it was denied. However, when I refresh, wait for it, you are hacked. So there you go. There's compromised integrity. Availability, we're not ready to DOS this yet because we still have more demos to do. But availability, I could drop tables. I could drop the database. I could delete data. Do a lot of damage with drop statements and inserts and modifying data. All right, in addition to that, okay, a little bit more remote code execution. This particular connection has system privilege. It doesn't get any better than that on a Microsoft box. So I can do anything I want with the command shell. For example, add a user account to the operating system. Submit. Access is denied. Actually, it worked just fine. Add it to the administrator's account. Oops, didn't want to do that. It says access is denied. However, look at the local users and groups. Oops, backing up. There's the hacker account, member of the administrators group. All right, now again, I'm using an older OS on this just because the application that is set up for it is extremely simple code based and straightforward. You have the same vulnerabilities on a 2022 machine with the same code. One of these days, I'm going to map this nice, simple application over to the 2022 platform. But for the time being, I'm going to use a legacy OS, nothing to do with it being an old operating system. Might have something to do with the default installation of that version of SQL, since it tends to be more functional on the turnkey installation than it needs to be. So we might have some unnecessary functions enabled, but other than that, it's just the way the application is actually implemented. All right, so there's a couple examples of why bother about SQL injection. All right, we're not done by any stretch. So we've seen remote code execution, information disclosure, authentication, authorization bypass, compromise, integrity, availability of data, and it just goes on and on. All right, so we've seen that it's the post request that is typically the target of a SQL injection. Most injections land in the middle of a select query. They get hijacked, they're completely altered, throw a semicolon in there, cap it off, fill in whatever you like, and then tack it to comment out the remainder of the query. All right, some other examples. Union statements. Okay, really quickly, unions will join the results of a query with the original query. So more or less, you can tell it to overwrite the original query with information that you're requesting in the union statement. So for example, product name and quantity per unit here are being overwritten by username and password. So this particular page is set up to return the results of a query back in a response page, but it's supposed to be giving product names and quantity per units, not usernames and passwords, which you can see right here. So sometimes the query comes back, sometimes you have to drop it somewhere and browse to it, like I showed you with the HTML files, or you can drop it to a text file, download the text file, or you can drop it to a text file and then import the text file into the database and query it. Sometimes you got to be a little bit creative with where you retrieve the results. On error-based SQL injection, the errors give away lots of information, like failed to convert this, failed to group this, failed to union this. When you specify a generic data type and it resolves back to the proper name for it, database or table and so forth, that sort of thing can be communicated through error messages. So error-based in general, errors should be suppressed. Right? When an application goes live, you should have very simple, plain error messages. Oops, you've encountered an error. Oops, you've encountered an error. Oops, you've encountered an error. With no detail, it gives way too much information to the attacker. Error messages are great while an application is in development, but once it goes live, make everything nice and plain. All right, blind or inferential. So when you get no definitive error messages, you have to kind of guess at what the results are, what you're not seeing. So the courseware is going to introduce this concept, and then it's going to kind of walk away from it for a few slides, and we're going to swing on back to it. But a generic page like this one here, access is denied, access is denied, access is denied, tells you nothing about what the error was. So we're actually going to ask some true-false questions and kind of poke at some things and determine it by the response time of the access is denied page. So hang tight, we're going to come on back to that. All right, so the generic page, and they are time intensive since you're looking at a time delay or an immediate response page. So, oops, you've encountered an error versus, hey, you've got an unclosed quotation mark before a character string, et cetera, simple error-based versus blind. Now, blind in general is really just no definitive response back, but quite often it's the delay in the response time. So a wait for delay statement in Microsoft tells it to wait X number of seconds or minutes before responding. Benchmark in MySQL tells it to do something X number of times, which results in a time delay. So long story short, I'm going to ask true or false questions, and if I'm right, wait 5 seconds before responding. If I'm wrong, just respond immediately. And like I said, they're going to tease it a little bit and then walk away from it. We're going to swing back to it here in just a second. Our union injection. Okay, unions can actually display the results in a response page, or they can elicit an error or a proper resolution or a resolve. So there's always a DB underscore name, there's always a table underscore name, but the specifics of that might be returned in a response. So when I say union select all DB underscore name, it swings back with not DB underscore name, but the actual database name. Coastal Bank, Good Shopping, Movie Scope. So the DB underscore name is resolved to the actual name and returned in the response. Same thing with table names, column names, field names, and so forth. All right, the same thing with convert statements. Now, these are actually error-based. There's different data types in SQL. So when you try to convert one data type to another incompatible data type, it's going to scream back at you and say, can't do that. It's not compatible. So when I say convert a nvar char to an int value, DB underscore name, it says, no. Couldn't convert Coastal Bank, couldn't convert Movie Scope, couldn't convert Good Shopping back to a column of data type int. So it gives away in the response the actual resolved proper name for the database. All right, same thing with the table names and so forth. All right, you can also then ask trial and errors or true false questions. So let me demonstrate. All right, on my 2022 machine, the first thing we're going to do is try to figure out the length of the data that we're trying to discover. All right, let's just say that I'm going after the database name, which the database name is actually Coastal Bank. Now, we looked earlier at the ability to just do a query, return the results, use those results. That's not always possible, right? We don't always get the results of the query back. We may not be able to browse to them. So in blind, we're going to use that response time of the error page. So the first thing I'm going to do is check for the length of the data type. And it's a little cryptic, but if the length of database underscore name equals 1 character, wait for delay. Submit it. Okay, it did not wait for delay. It didn't wait 5 seconds. It was an immediate response. It's not 1 character. Is it 2 characters? Nope. Is it 3 characters? Nope. Is it 4 characters? No. 5, no. 6, no. 7, no. 8, no. 9, no. 10, no. 11. Ooh, 1001, 2, 3, 4, 5. Hey, 5-second delay. I guessed right. 11 characters. So now I know it's 11 characters. Now it's kind of like playing hangman. What's the first character? What's the second character? What's the third character? And you're doing that one at a time. And this can be excruciating because you're guessing each one at a time. Is it A? Is it B? Is it C? Is it D? Is it E, etc. So we're using ASCII decimal codes. 97 is an A, 98 is a B, 99 is a C, 100 is a D, 101 is E, etc., etc. So I'm going to guess, is it A? Nope. Is it B? Nope. Is it C? Nope. Oh, wait a minute. 1001, 2, 3, 4, 5. Yes, it is C, Coastal Bank. 5-second delay, guessed correctly. All right, and then you're going to go to the second character and the third character. So I'm so conditioned to using the old Movie Scope database, I was thinking, yeah. So it's Coastal Bank. I would know that by running 11 separate length queries with a trial and error A, B, C, D in each one. So that's why you script things out, and that's why you use automated SQL injection utilities, which automate that process. But that's how it works manually, and that's what we're demoing. So manual, methodical, and slow. So that's what blind injection might look like. There's other flavors of that, but you can use the same concept and the same technique for all different types of data types. Guess the length, guess the characters. Now that might be, again, a little painful. Is it A, is it B, is it C, is it D? So expression searches can expedite that process. An expression would be like, hey, is it between A and M? It is. Is it between A and F? It is. Is it between A and D? It is. Is it C? And you can kind of narrow things down. So fewer queries, more efficient search versus is it A, is it B, is it C, and so forth. All right, creating database accounts. You can create accounts of the web application. You can create accounts on the database management server, and you can also create accounts on the underlying operating system. So 3 different code bases or account bases to create user accounts. And remember, step 4 of the hacking cycle, step 3 of the hacking cycle is to gain access. Step 4 is to maintain access. And one way to do that is to create user accounts to access. All right, interact with the operating system. We've already seen the XP command shell, but the results of that command shell, if I ran an ipconfig, where are the actual results going to go? It's not a terminal window, it's not a web shell, so you'd have to drop it to a file and then browse the file. Pretty much what I did with the spmake web task when I sent the results of the query to an HTML file. All right, there's also loading the file, which is a MySQL function, where you can actually call things like the etc password file. The etc password file is interesting because it's the user accounts on a Linux box. So that helps to enumerate users. There's also a SQL query which will generate a web shell, potentially, which we talked about last class. The web shell, remember, is an uploaded page that gives you a command shell. Very basic PHP syntax. And this particular query might send the results of that into an out file and create it for you through a database query. Pretty cool. All right, finding and bypassing the admin panel of the website. That's just Google Dorks, Google hacking. All right, so you're looking for well-known strings to identify admin pages, and then you can trial and error all sorts of different true or false combinations to authenticate, to get an authentication bypass. So one more quick example of that. Let me back up. Okay, when I do a 1 = 1 statement, all right, it's anything that rings true. Okay, 1 = 1. If 2 is less than 1, doesn't work. How about 2 is greater than 1? It works. So to evade IDS signatures, you probably want to avoid using 1 = 1, since that's a pretty common authentication bypass. Use something else that just is logically true, and you're less likely to get detected by an intrusion detection system. And we're getting ready to talk about that. Even though we've had our evading IDS firewalls and honeypots discussion, we've got a couple great slides to illustrate different types of evasion for SQL injection. All right, so getting an OS shell, I actually just talked about that with a query. All right, then there's creating a database backdoor. There's command shell interaction, which we've seen examples of all this. And then your SQL injection tools. Now, in your lab, you're going to use SQL map, but only after doing some manual SQL injection on Microsoft SQL Server. So in your labs for tonight, you'll do a SQL injection attack against MS SQL using SQL map. All right, and actually, I'm sorry, there's an earlier lab where you do that manually. I actually was going to add that back in. And then detecting SQL injection vulnerabilities using OWASP Zap, which I need to add that back in because that's a great lab. Or evading IDS. So for the longest time, for decades almost, teaching this course, evading IDS firewalls and honeypots came after SQL injection. It came after hacking web applications, and it came after hacking web servers, which all 3 of those modules have great examples of evasion, Unicode encoding, web application evasion, and then most definitely SQL injection. So as we mentioned in module 12, we'll be seeing some cool slides later on. And here's a few great examples of evading IDS. But remember, the key to evading IDS is to not let the IDS see the signature it's trying to match, right? But preserve the functionality. So different types of evasion: inline comments, character encoding, string concatenation, obfuscated codes, manipulating white spaces. We have a slide for each one of these, so let's take a look. All right, inline comments. Okay, slash asterisks, asterisk slashes are comments. They're ignored. So what would normally be union select password from to the IDS looks like extra data. To a receiving system, it just ignores it. So it ends up deleting the slash asterisks, and it becomes union select password from users where password like admin. So the IDS sees something more. It looks padded out. It's almost like the insertion attack we talked about in module 12. And then character encoding uses the decimal ASCII codes instead of the actual ASCII characters. So for example, 47 is a slash, 101 is an E, 116 is a T, 99 is a C, 47 is a slash, 112 is a P, 97 is an A, 115 is an S, S, W, and D. Look at that, that's the password encoded in decimal encoding. All right, same thing with hexadecimal or string concatenation. In a string concatenation, you're carving things up, you're double piping them to stitch them back together, but in the eyes of the IDS, that's extra stuff. It doesn't match the signature. The receiving system, it's things to be ignored or reassembled, and it actually executes like a unconcatenated query. So it puts it all back together, but the IDS sees extra data. All right, then you get transpositional shifts and substitutional shifts. You can get really creative and crazy with this. As long as it gets reassembled correctly on the receiving system, that's all that matters. White spaces, no bytes is extra data according to the IDS. There's actually data there, even though it's a white space. Hex encoding, hexadecimal encoding. So obfuscation in general is alternative encoding. You're trying to get the receiving system to interpret it correctly, but you're getting the IDS to not specifically match the patterns. And we talked about case sensitivity and some other things in module 12. Same thing applies here. Our URL encoding, which is just hexadecimal with percentage signs. No bytes, percentage 00s, it's still data. And then case variation. All right, remember the easy fix for case variation is a no case argument in the snort rule, which ignores case sensitivity. But union select user ID password from adminware doesn't match all lowercase in a SQL in a snort rule. All right, declaring variables in the middle of a statement. Okay. Then IP fragmentation, which we talked about that in module 12 as well. Remember that IP fragmentation is chopping things up, and if they don't get stitched back together, they're little puzzle pieces that don't reassemble the signature that the IDS is trying to detect. All right, and that's going to wrap us up for SQL injection, which is a brief introduction in the grand scheme of things. There is a ton to SQL injection. It's one of the most widespread application vulnerabilities for the last 20 years. It's not going away anytime soon, and it does give a great example of other types of injection.